Okay, Dimitri, could you go to the Blocker Media Center? You know where that is?
Over there.
Straight in the front hall next to two big front rooms. Tell them this isn't working.
Oh.
I'd get somebody to come over. Okay, so what is this? This is A minus BI and divided by the length of Z, which is A squared plus B squared. So I'll write it as A over A squared plus B squared minus B over A squared plus B squared I. And now I'd like to know what is the length of this reciprocal. Okay, so I think I'm too low on the board. Start a new board over here. What is the length of the inverse? It is the square root of the sum of the squares of its real and imaginary part. See, when you took Z and asked for its length, I take the real part squared, the imaginary part squared, a plus sign between them. I don't square the I in doing this. Just take the real number B. That's multiplying the I. So that's what I have to do over here. So here's the real part. Here's the imaginary part. I don't use the I.
Wait.
So I've got an A over A squared plus B squared for that part. And I have a minus B over A squared plus B squared for that part. And I do the square, the sum of the squares of the two pieces. Yes?
What's happening? I came.
You guys came in a few minutes late. Let me do it. I was reviewing what we did last time. Hi. Hi. I don't see it doing before. Okay. What we did last time is we did products of complex numbers, used the distributive rule to work it out. Over here there was an I squared, which became minus 1. You remember that from last time? Okay. And then I regrouped them. This part and this part are real. This part and this part are imaginary. So there's the real part and there's the imaginary part. And last time I also defined the conjugate of a number, of a complex number, by flipping the sign of the imaginary part, right? And I calculated Z times Z bar, and it just became A squared plus B squared. Now it's working.
What was not working? It was on a different source.
Ah,
Way too long time.
yeah, it's working. And I need to get the projector turned. And is there another control? There it is. All right, good, thank you. Yes, sir. Have a nice day.
You too.
All right, so we multiplied Z and its conjugate and found out it was purely real, and divided by it, and we found out that the product of Z and this combination was 1. Hence, this combination is the thing you multiply Z by to get 1, so that's called the reciprocal or inverse. Okay, and here's its formula, and I also define the square root of the sum of the squares to be the length of Z. And so I now want to know what is the length of Z inverse. Okay? And you find the length of any complex number by taking its real part and its imaginary part and doing the sum of the squares, square root of the sum of the squares of the real and imaginary parts. And that's what I'm doing over here. Here's the real part, here's the imaginary part. So now I have to work that out. Equals square root of A squared over A squared plus B squared squared plus B squared over A squared plus B squared squared. They have the same denominator, so I put them over a common denominator. A squared plus B squared over A squared plus B squared squared. but there is a number and there's the number squared. So one of them, they cancel. So it gives me the square root of 1 over a squared plus b squared, which is 1 over the square root of a squared plus b squared. We do a square root of a quotient by taking the square root at the top and the square root at the bottom. Right? And so we now see that that is 1 over the length of z. Yep, what, Martin?
Never mind.
So the length of the reciprocal, not surprisingly, is 1 over the length of z. Okay? Not a surprise, but we had to compute it and see that it did work. Okay? Okay. Now there are, so we've got a bunch of different numbers, and I want to see, where is this stuff? Dimitri's. Ah, I bet I have it on here. No, maybe I don't. Where do I have it? Dropbox.
Our my methods are in Dropbox.
Oh, no, but it's here.
Okay.
It's on here. So let me-
The C isn't all the way down.
I know that. I will when I'm making sure, once I get it to work. Okay, open folder and worksheets 1-4, complex. Let's sort by type, matrix, complex. This was written by Dimitri. Let's look at the algebra in rectangular coordinates and the plot in rectangular coordinates. That's that one, and that's that. And now we'll bring the screen down the rest of the way. Okay, let's see. I guess we could use a little bit of different lighting.
Oh, yeah.
All right, so this says here are two complex numbers called z and w. And I don't like the choice of that because z is purely real, -5. So I'm going to pick another pair. Okay, -5 minus I and 4 plus
Can't
I.
see the I.
Uh,
It's hard to see.
I know, and unfortunately I have no way to enlarge this. Okay, it works fine on your computer, but I don't have a way to enlarge it on the screen. Sorry about that. So I will write it on the board, which is also hard to see because the lighting in the room. But this outlet, which you can access, it's in the list of them. Oh, and I believe they reactivated my temporary drive, so you can get back to these again. We'll have to try it again later. But this asks you for all the different facts about z and sometimes w. Okay? So z is -5 minus I. Okay? And the first one it asks is the real part of z. Everybody, what's the real part of z?
-5.
-5. The real part of z, there's the notation we use, is -5. The imaginary part of z,
Minus I.
you don't say the I,
-1.
just the number that's multiplied with the I.
Wait.
-1. The real part is this real number, the imaginary part is this without the I. This is -1 times I. So the imaginary part is -1. Yes, Lou?
What exactly is I? I didn't quite get I.
Square root of me.
I is square root of -1.
So why did you write that?
Why don't I write it here? Because the definition of the imaginary part of z is the real number that multiplies I in the formula for z.
Wait.
We don't include the I in the imaginary part. It's just a convention. Okay? So show the answer here. The real part is -5. The imaginary part is minus 1. That is because this is minus 5 minus 1 times I. That minus 1 is the imaginary part. We don't include the I. Okay? It's just a
Oh,
convention.
wait.
Let's look at W. W is, no, let me give a different one. U is 3 plus 4I. The real part of U, Luke, is what?
3,
And the imaginary part of U,
negative, no, 4.
just 4.
4.
Okay?
Okay.
You read off the real thing and you read off the imaginary thing and throw away the I.
Oh, so you multiply it by negative 1 because it was subtraction?
Yes.
Okay, I get it now.
All right, so we don't need U. Then we have W up there. It doesn't ask for their pieces. All right. Now then we have the magnitude of Z. The magnitude of Z. Here's the real part. Here's the imaginary part. What's the square of the sum of the squares? Come on, everybody.
Okay,
36.
Not 32. Square this.
25.
Add this square.
26.
Add 1. What do you get?
26.
27.
And then you take the square root. Okay? All right, the one, and now we need Z plus W. So over here we have W. Can you see the board, or do I need to turn the light on? You can see? Okay. W is minus 4 plus I. So Z plus W is, add the real parts. What do you get?
9.
Minus 9, add the imaginary parts.
0.
0, so I don't need to write anything. So Z plus W is minus 9. Let me do my shows here. So the magnitude of Z is square root of 26. We'll come back to the argument. Z plus W is minus 9. And we need to do Z times W, which is Z times W is minus 5 minus I minus 4 plus I is product of the first, which is 20. Outers is minus 5I. Inners is plus 4I. Less. What is minus I times I?
Negative I squared.
Negative I squared, which is
Positive 1.
plus 1. So the whole thing is 21 minus I, which is what it told us. Okay? Then we need the conjugate of Z. So what is Z bar?
Negative 5 plus I.
Negative 5 plus I. We just flip the sign on the imaginary part. Okay? And we need the Z inverse, which is it's this number minus 5 plus I over 26. The length of Z squared. So, show them. Okay? So it's minus 5 over 26 plus 1 over 26 times I. Okay? And so the only one of those you don't know yet is R or Z. And I have to talk about plotting complex numbers first. So, talk about plotting. I'm back to the argument of Z there. If I have Z equals X plus I, Y, I draw a plane, I put X here, there, and Y there, and I plot Z is this point. This length is X, this length is Y. That's called the complex plane. Okay? The real numbers you put along the line, complex numbers you graph in a plane. So for example, 4 plus 3i appears 4 over this way, 3 that way, and this is 4 plus 3i. Okay? Minus 3 minus 2i, minus 3 minus 2. This is the point, minus 3 minus 3 minus 2i. Okay? So it's no different than plotting a point in the plane with x and y. You just, instead of doing the ordered pair, minus 3 minus 2, you write it as minus 3 minus 2i. Okay? Now let's see, where are all the points whose length is 1? That says the square root of x squared plus y squared is 1. If z is x plus iy, we take the length of z is the square root of x squared plus y squared, right? And setting it equal to 1, what is the shape in the xy plane? Square.
Well, half of a circle.
Because you're demanding the positive square root.
Yeah. What about
If we use negative numbers here, like minus 1 over square root of 2 with minus 1 over square root of 2, it still adds up to 1. So you're not restricted to positives only. So what did you say?
circle?
It's a circle. The equation of a circle is x squared plus y squared equals radius squared, right? And that's the radius of the circle. So this is a circle centered at 0, 0, centered at the origin of radius. What's the radius of the circle? 1. So here is the circle of radius 1. It is the unit circle in the complex plane. What is this class called? There it is. Okay, that's the unit complex circle. Okay, and every point on that circle is a complex number of length 1. Okay? Now, what are the coordinates of that point? Suppose we're at that point at an angle theta, and the radius is 1. What are the coordinates? If you think of it as an x and y, what are the coordinates of a point on the unit circle at angle theta? Goes back to our trig stuff. We draw the
Cosine
triangle.
theta.
What's the x coordinate? That's right.
Cosine theta.
Cosine theta for the x component, and what's
Sine
the y?
theta.
Sine theta for the y piece. However, if I do it in terms of complex numbers, that point is cosine theta plus I sine theta. Okay? That occurs so often that we give it a new name. CIS theta. Cosine plus I sine is abbreviated CIS, CIS. So cis theta means cosine of theta plus I times the sine theta. That is a complex number whose length is 1. We should check it. So we'll come over here and do that. So suppose the angle is 30 degrees. Then here is a 30, 60, 90 triangle. What are the sides? What are the sides of the 30, 60, 90?
1 square root of 2 and 3.
1, 2, the square root of 3.
Oh,
1, 2, the square root of 3. Right? So then the point at 30 degrees on the unit circle has coordinates in x and y. Cosine of theta, cosine of 30 degrees is What's cosine of 30 degrees? Yeah? What's cosine of 30 degrees? What over what? Adjacent over hypotenuse. And the sine? What over what? No. Opposite over hypotenuse, for sine. 1/2. Right? And as a complex number, that is the point square root of 3 over 2 plus 1/2 I. What is its length? The length of the square root of 3 over 2 plus 1/2 I is equal to the square root of the sum of the squares of its real and imaginary parts. Its real part is square root of 3 over 2. Its imaginary part is 1/2. Right? So that becomes the square root of 3/4, squaring that, plus 1/4. What's it add up to? 1. That says this point is on the unit circle of the complex plane. Okay? More generally, if I have a point at angle theta, this is the point cosine theta sine theta, or cis theta. So what is its magnitude? The magnitude of cis theta is the square root of the sum of the squares of its real part and imaginary part. What is the real part of cis theta?
Cosine theta.
And what's the imaginary part?
Sine theta.
So that's what we have to take the square of the sum of the squares of. Cosine theta sine theta. Square of the sum of the squares of those two things. What's cosine squared plus sine squared? 1. Square root is 1. Cis of any angle is 1. We use radians. Over here I use degrees. Technically we should be using radians. Okay?
Technically.
The point in the xy plane has rectangular coordinates x and y, polar coordinates r and theta. Okay? R is called the distance from the origin, theta is called its phase or argument. Likewise, with the complex number, there's the real part, there's the imaginary part, there's the length of z, which is the distance from the origin, the radius away from the origin, and then the one more thing is the argument, or phase of z, is the angle it's at, which is arc tan of y over x, possibly plus or minus a pi, depending on which quadrant you're in. Okay? But the important thing, it is the angle of the point. Okay? And so the number z, let's see if I can say this again. Let's do it in general. Here I did a point on the unit circle. Now I want to look at a general point. This is an angle theta. This is a radius r. This is a point x comma y. X is equal to r cosine theta, and y is r sine theta. That's just polar coordinates, right? Now let's do it in complex numbers. This is the point z, which is x plus iy, which is, and r is the square root of x squared plus y squared. It's the distance from the origin to that point. Right? And now this, x plus iy, I can put in those things. R cosine theta plus r sine theta times I. X plus iy, I wrote the I last, doesn't matter. Notice the r factors out. And this is r 6 theta. There is the magnitude of the complex number. There is the argument of the complex number. Every complex number can be written in rectangular form or polar form. The rectangular form has I, x, and y. The polar form has r and theta, magnitude and phase, or argument of the complex number. Okay? Do you remember when we talked about sine curves and shifting them and raising them, and we talked about amplitude, magnitude, period, and phase shift? That's the same phase. It is the angle in the sine curve, and when you shift it by adding something, it's a phase shift. Okay? And so it's the same word, same meaning. And so here we need the argument of z. And so what is the argument of z? It is arctangent. So for that z up there, it is, z is minus 5 minus I. It is the arctan of y, which is minus 1, over x, which is minus 5. And we have to, they're both negative numbers, so we're in quadrant 3, so we have to subtract pi. So if you have your calculator and compute arctangent of 1/5, and then subtract pi, and you have to do it in radians. Okay? You ask what angle has tangent equal to 1/5, and then subtract pi to get it into the third quadrant, you will have the argument, and it turns out to be minus 0.936 pi. Okay. And so that's the sort of the only confusing one of all of these. Then there is another maplet, also written by Dimitri back there. Not a good choice. There we go. Here we have 8 points. And we're given the complex number 2 minus I. Which one of these 8 points is 2 minus I? The complex number z there is 2 minus I. 2 is the x coordinate, minus 1 is the y coordinate. Right? Which of these points is 2 minus 1? B. Okay. Yes, Mark?
It says his version roughly for August 2013. It's not August 2013. It's still due.
Yes. Well, this is going to be released for commercial purposes next month.
Ooh.
Okay? And anyone who manages to write a maplet that I can get polished up, it'll be included and given out in August 2013. Okay? So we say that this one is B, and we check it, and we're correct. All right, where is minus Z? So that was Z, where is minus Z? First of all, what is minus Z? If Z is 2 minus I, what is minus Z?
It's E.
Negative 2 plus I.
Negative 2 plus I. Which graphic? Which point?
D.
D. Let us check that one. We claim that is D. Check it. Ooh, what do you know? We're right. Z bar.
E.
What is Z bar?
Change the sign of the
Imaginary part. So what number do we get? 2,
1
2 plus I.
plus I.
Where is 2 plus I? E. Thank you. You had it already before. Okay. E. Check. Where is minus Z bar?
Wait, what does it mean, bar?
Bar is conjugate. I lost what's up here. Conjugate is if z is x plus I y, z bar is x minus I y. Unfortunately, the computer doesn't have a way of putting the bar over it. So I wrote it, caret bar.
So, like, it replaces the signs?
It flips the sign of the imaginary part. Okay? So if you take 2 minus I, flip the sign of the I part, what do you get?
Plus I?
2 plus I. That's what z bar is. Where is 2 plus I on this graph? Which point?
What?
Which one of these 8 points is 2 plus I?
2 plus I, negative 1.
2 plus is this way, I is that way.
Oh, E.
Yes, E. Okay. Now, what about z inverse? Z to the minus 1. How do you find z? Yes?
We skip negative z bar.
Oh, we should have done negative z bar. I'm sorry, what is negative z bar?
H.
E was there, H is its negative. Okay, H. Check. All right, z inverse. Z inverse. So z inverse is z bar over the length of z squared. So what's the length of z? Square to the sum of the squares of the components. What's the length of z?
5.
5. So then we have to divide every component of z bar. Z bar was e. We have to divide everything by 5. That just shrinks it to a. Okay? It's 1/5 of the way out. Okay? So it's the line segment from the origin to E and take 1/5 of that length. So this one is A. Okay, what's minus Z inverse?
C.
C. Good. What's Z bar inverse? Where was Z bar? Z bar was E. Z bar inverse. You have to bar Z bar, so that takes you from E to B, and then divide by the length, which is, puts us at G. Okay? So Z bar inverse is G. And finally, minus G is F. Okay? Now I should check. Okay, new point. Okay? So we'll do it once again. Minus a third plus 1/3 I. Where is minus a third plus 1/3 I?
B.
Which one?
B.
Does everybody think it's B? Minus a third for the x coordinate and 1/3 for the y coordinate. B. Okay, so that one is B. Good. And now minus B.
A.
You flip across. X and y both get flipped their signs. So we're now at A. So we're minus it. Z bar. What's Z bar? Where's the bar of B? You flip the sign of only the imaginary part, the y component.
Yes, E.
E. Okay, so that one should be E. Minus Z bar. What's minus E? G. Check it. Where's Z inverse? So Z was B. We need B's inverse. First, we have to take the conjugate, which is E.
Oh, A.
And then we have to stretch or shrink it by the length. The length of this thing is less than 1, So dividing by that actually stretches it, makes it longer. So it's H. Dimitri, we're not having any trouble with those funny appearances of
Yeah,
H's.
I think it's the new maple. I think.
Maybe it's 16.
Yeah.
I don't know. Could just be the graphic. The display is not having a problem. Okay, minus Z inverse. Where's the minus of H? C. Okay. And C. Is this sort of fun to be finding these?
A little bit, yeah.
Little bit. It's
Kind
like a
of,
game.
Maybe.
Okay. Z bar inverse. So here is Z bar, which is E. Z bar inverse.
H.
So this is Z bar is E. Its inverse, you take its conjugate and then flip its, get the reciprocal of its distance from the origin. So this is less than 1 from the origin. This is more than 1 from the origin. So it goes to D. And finally, minus D is okay. And the hints here give the definitions. Okay, tell you what these things mean. And there it's using the notation INV for inverse instead of minus 1 power, and it's using CONG for conjugate. Oops, hint. The conjugate of Z, instead of calling it Z bar, it's calling it conjugate of Z. Okay? It's just to get used to all the different notations for these same things. Okay, now, I know I'm going fast. You just learned about cis theta. But now I have to, because we only have 3 meetings left, I really have to move. And so now I'm going to see what is the product of 2 cis's.
2 cis.
Yes, we have a pair of them over there. 2 cis's. Okay. Okay, so suppose I take CIS alpha times CIS of beta. So I have 2 different angles. I have the complex numbers of length 1
Is
at 2 different angles.
cis always 1?
The length of cis is always 1, the magnitude of that. Because cis is cosine theta and sine theta. Cosine alpha and sine alpha for here, the length of that is going to be square root of cosine squared plus sine squared, which is 1. Okay? What happens, what do we get when we multiply 2 complex numbers of length 1, one of them at angle alpha and one of them at angle beta? So let's multiply it out. Cosine alpha plus I sine alpha. Cosine beta plus I sine beta equals. This is probably the most important computation of the class. Not necessarily the hardest, most important. This one times this one. Cosine alpha cosine beta. Outers is I cosine alpha sine beta. Inners I sine alpha cosine beta plus less. I squared is a minus 1. Sine alpha sine beta. And now we group them into the real part and the imaginary part. Cosine alpha cosine beta minus sine alpha sine beta. Cosine alpha sine beta plus sine alpha cosine beta. Would everybody read the trait functions with me as I point to them?
Cosine, sine, sine, cosine.
Let's do them the other way. Sine graph, and what does it do? What's it say this is?
Cosine alpha plus beta.
So cosine of alpha plus beta plus I times
Sine alpha.
sine of alpha plus beta equals cosine plus I sine cis of alpha plus beta. Whoa, he says. Tony liked that. Cis of alpha times cis of beta is cis of alpha plus beta. That is easier than the trig graph and has all the same information. Cosine plus I sine of variables. When you multiply the functions together, you get the function of the sum. Okay? And so let's look at a couple extra cases of that. Suppose alpha and beta are equal. CIS alpha. CIS alpha is CIS of
Oh, it's worth it. 2 alpha.
So let's put the square on this one. Cis alpha quantity squared is cis of 2 alpha. Cis of alpha times cis of 2 alpha is cis of 3 alpha. Right? You add alpha and beta to get over here. But cis of 2 alpha is cis of alpha squared. Cis alpha squared. All is cis of alpha all cubed. In general, CIS alpha raised to the nth power is cis of n times alpha. Whoa. Isn't that really cool? This cis function is extremely powerful. Where have you seen that kind of a rule occur previously? That you have a function and you raise the function to the power, and what you do is you get the same function with n multiplying the argument. Have you ever seen such a function before?
Sure I have, but I just never really.
Suppose we have f of x equals 2 to the x.
Okay, that.
Okay? What is f of 2x? It's 2 to the 2x. But f of x squared, just to be careful, is 2 to the x squared.
All right.
Do you remember how to raise powers to powers?
Oh, you multiply them together, so it's
You multiply what?
the exponent, so it's 2 to the 2x power.
And these two things are equal.
I don't know what that property is called.
It doesn't have a name that I know of. It's one of the properties of exponents. Okay? B to the A to the C is B to the AC. Right? And the function, any base to the x, has the property that if you replace x by n times x, let's go one step further, raise, turn off screen temporarily. Is that turned off?
Yeah.
Okay. Let's do it with an n. F of x is, so f of x is some base to the x. F of x raised to the nth power is b to the x to the n which is b to the nx,
Take with yourself.
any questions about that? Is equal to f of nx. Okay? So this cis function has the same properties as exponents. And in fact, it is an exponent. It is something to the power alpha. What? Okay? So cis of alpha is some base to the alpha. And we would like to know what the base is. And I don't have any really good way to justify what the base is. It is a definition in some sense. Okay? And I'm just going to tell you what the base is. The base is e to the ith power. You're laughing, and you're right. Where did that come from? Nowhere. Have you seen this before? Any of this before? Anybody? No. You saw a little bit of this. Okay, so cis alpha is e to the I alpha. And we usually do it with the letter theta. So let me write it with theta in there. E to the I theta is cosine theta plus I sine theta, also known as cis theta. This is called Euler's equation
Why does Euler have so many things?
because he did so much. Okay? What do you get when theta happens to be pi? E to the I pi. What's the cosine of pi? Cosine function. What is it? What is the sine of pi?
Zero.
E to the I pi is minus 1. E to the I pi plus 1 equals 0. How many of you have seen that equation? Anybody?
No.
That's also called Euler's equation, but it's really a special case of this one. Okay? This is a fantastic equation, and you'll see it on people's t-shirts. It includes every one of the important constants of mathematics. 0, 1, I, pi, and e. They're all in there. It includes addition, multiplication, exponentiation, and equality. All in the same equation. And it's a true statement. E to the I pi is minus 1. Okay? And it comes out of this. And so that, if I write it in shorter notation, is really easy to understand. E to the I theta is CIS theta. You raise it to the power n. CIS theta raised to the nth power is e to the I theta raised to the nth power is e to the I n theta, which is cis of n theta. Okay? This is the notation mathematicians use. Only sort of when you're learning it do you use cis theta. Okay? And in a longer course on complex numbers, we would probably have spent 2 or 3 weeks just calling it cis theta until we decide to change our point of view and start calling it e to the I theta. Okay? But I only had one lecture to get you through that. Okay? I probably did a lot of stuff today. Am I right? Okay, so we went from the definition of complex numbers all the way through to Euler's equation. What else is here in these maplets? There are two more maplets
When we go to
we
the
can
computer.
look at.
10, 15 minutes.
And you don't have anything up there
10
right
minutes.
now. There we go. Let me turn
Maybe
that
we go
back
now.
on.
So maybe we go now.
Back down again. Complex number.
Please turn on PowerPoint.
You have questions? Yes, Lou?
Actually, I took Euler's theorem and rearranged the numbers and symbols and kind of
Yeah.
a few of them, and you can make it spell Euler.
How do you do that?
You have to like cross over, you have to kind of make them smaller and bigger and then rearrange them.
Okay, you sound like a Dan Brown mystery.
See, I don't know name up.
Okay, this is the graphical description, but now it's pretty much the same problem, but instead of giving the complex number as real and imaginary parts, we've got it in polar form. So z is 1/4 e to the 7/6 I pi. So what is the length of the vector or the complex number z? How big is it? What's its magnitude?
Yeah.
You're looking at the graph. I just want to look at the number. E to the I alpha, e to the I theta is a complex number of length 1. So what's the complex number z? What's its length?
I can extrapolate.
1/4. Okay? That means the point should be 1/4 away from the origin, the radius. It's on a circle of radius 1/4. So that tells me it's CF d or h. Right?
Wait, what time is it?
It is 3:30. And the map, if I didn't have these things disappearing, it would be there. There it is, 3:30, down in the bottom right corner. All right. And now the angle, the magnitude of z is 1/4. What is the argument or phase of this complex number? Just look up there in the exponent and get the coefficient of I. It's e to the I theta. Theta is the argument. So what's the phase? 7/6 pi. Pi is 180. 7/6 pi is bigger than pi. So which dot is at 7/6 of pi? H. Okay? So you look at the magnitude and the argument of the complex number, and you can figure out where it's plotted. So z is h. Check. Okay. Now where is h's conjugate? How many vote for C?
Oh.
How many vote for F? I heard F. Retracted your F's. It's C. All you do is flip the complex part. What is the phase of the complex number? Of the conjugate? The original one was 7/6 of pi. What's the phase of the conjugate?
Negative 7/6.
Negative 7/6, that would do it. However, another way of saying it would be 5/6. Okay? By the way, when you do the conjugate of e to the I theta is e to the minus I theta. All you do is replace the I by a minus I. The same as x plus I y bar is x minus I y. You replace the I by minus I. Here, when you conjugate the complex number, you replace the I by minus I. You also have a real number out front. That doesn't change. Okay, the magnitude. Yeah, another question. Sure. Right around past the elevators. Okay, so where's minus z? Z was h.
F.
Minus z is f. The conjugate we said was c. Where is minus z bar? D. Where is Z inverse?
B.
You start from H, you take its conjugate, which puts you at C, and then you have to stretch it. So it's the vector for the R and C, either you stretch and shrink it. If it is outside of the unit circle, you shrink it. If it's inside the unit circle, you stretch it. Okay? And so you end up at B for the inverse. Let's see. Correct? I am. Minus B. G. And Z bar inverse. So Z inverse was B, its bar. The bar of B is A. Okay? So that one is A. Check it. And minus Z bar inverse. E. So this does it all in terms of polar coordinates identifying all 8 of these quantities.
Here they anyway.
Plus or minus, bar or not bar, inverse or not inverse, and all the combinations of those things. Okay? Then there is one more complex algebra in polar coordinates. By the way, the reason Dimitri made these was his mother is a lecturer in the math department. She came to see me and said, we teach differential equations, which is a sophomore or junior level course in college. Comes after calculus. Okay? And they need to use complex numbers in the class. And she said, all of my students are coming in and they've never seen anything more of a complex number than in the solution of a quadratic equation. Could you make me some maplets which would help them learn more about complex numbers? So I hired Dimitri, and he made these 4, and he's making more for differential equations. But these 4 are on complex numbers, and all of our sophomores and juniors never got complex numbers in high school. Even the honor students, I've asked them if they've seen complex numbers, and they said no. And that's why I figured I would teach them to you, because you need to know them eventually. And, so, yes, Luke, Mark, first.
You said you hired him, do you mean you,
I pay him. I have an NSF grant to write these applets, okay? And I pay him to make them. And
Yeah.
eventually, somewhere in the middle of high school, I'll be happy to start hiring people who know how to write these kinds of maplets. And that's why I'm teaching them to you. Okay? There are other programming skills which I need even more than being able to write maplets, like programming in Python. So if you learn how to program Python, you'll be more of an asset. Yes?
Would you pay someone to, if they made an applet that has absolutely nothing to do with math?
Yes and no. Okay? I'm also paying Dawson, who is not here today, but he's been helping out in the maple portion especially. Dawson is editing all the maplets and getting all the colors to match and all the layouts to match and error messages to match between different maplets before I come out with the release at the end of the summer in August. So I got to go through all 200 maplets and make sure they're all functioning in uniform fashion, so that when we sell it, it looks nice. Okay, so he's working on that, and so here's another one. Here are 2 complex numbers, both given in polar form. Okay, so I need the magnitude of z. Let me write z over here. Z is equal to 5 e to the minus 5/3 minus 5/3 pi I. What is the magnitude of z?
5.
5. The magnitude of z is 5. What is the argument of z?
Negative 5/3.
Negative 5/3 pi. Okay? Those you just read off in polar form. The next, let me click show. There they are. Oops, looks like the argument is 1/3. Negative 5/3 pi is the same as plus 1/3. So it asks for it at 2 pi. And you get 1/3 pi. So its argument is supposed to be between minus pi and pi. Okay, that's just a convention. Just like square roots give you the positive square root when you write the radical sign. Here it gives a number between minus pi and pi. That is not, so you have to shift it. Okay. Next, the real part of z.
5.
What is the real part of z? I don't need it simplified.
5e to the power of 5.
What is e to this? What's another name for that? 5 cis of minus 5/3 pi.
Jesus?
Right?
Let's get that.
And so, what is the real part of this number?
J.
5 what? I heard it out there. 5 cosine
Go to the
of this
bathroom.
angle. Because this is cosine plus I sine. Right? The real part is the cosine. The imagined part is the sine. So the real part is 5 cosine of minus 5/3 pi. And if you want to work that out, you can. Okay? And the imaginary part of z is 5 sine of minus 5/3 pi. Okay? Yes?
Go to the bathroom.
Yeah. Okay. 5 cosine of 1 pi over 3, which is another way of writing the argument. 5 sine of pi over 3. What is the cosine of pi over 3? Gotta draw the triangle again. Pi over 3, pi over 6. This one here is 60 degrees. This one there is 30 degrees. What are the sides?
1, 2, square root of 3.
1, 2, the square root of 3. So pi over 3. What is the cosine of pi over 3?
Opposite over hypotenuse.
1/2 cosine. Adjacent over hypotenuse. So this is 5/2. And the sine of pi over 3? So this is 5, the square root of 3 over 2. And let's see their answer. There they are. 5/2 and 5/2 of the square root of 3. Okay? And what is z plus w? That's the hard one. And let's skip z plus w and go to z times w. Polar form makes it really easy to multiply. The magnitudes multiply.
So 5e.
Z is 5e to the I something. W is 1e to the I something. The magnitudes are 5 and 1. So the product is 5. So the product is 5. Oops, 5 times e to the power of. And now the angles half. Remember the identity? It's not over here anymore. Cis alpha, cis beta is cis alpha plus beta. Or e to the I alpha, e to the I beta. What do you do with exponents?
And
right? The exponential notation makes it really easy to remember what it does. Okay? So if I multiply these together, I get 5e to the something, e to the something's added. So I get minus 5/3 I pi plus 2/3 I pi.
Negative 1/3.
The thirds go away. Minus 5/3 plus 2/3 is minus 3/3. Right?
Negatives.
So it's negative I pi. So negative I pi minus I times pi. And warning, I need to answer both questions. I'm going to put something in there and get it wrong. No. Simplify your product and recheck your sum. What is e to the I pi? Euler's identity.
Thank you.
I know. I've been coming fast and furious. E to the I pi is negative 1. E to the minus I pi is also negative 1. So that simplifies to minus 5. So we've got simplify the sum. I'm just going to do show. It didn't change that to a minus. But here's the sum. Let's see if it'll accept minus 5. Almost. You have correct sum, but simplify your product. Interesting. Dimitri, you got some work to fix something. Okay? Okay, now the imaginary, the sum doesn't simplify, and it's a real messy expression. And it's really hard to do when you're in polar coordinates. Basically, you got to convert them both to rectangular coordinates, then multiply them together